Thanks. So not counting co-Is and members of my home institution, I think there are 8 of you in the audience. So you'll get one slide each, essentially.
Nice.
Yeah. Let's see. Is this working?
Ricky, we're not getting the signal here. Jesus, I cannot believe how did we get to the moon?
Well, we did it without Wi-Fi.
That's the answer. Now?
Something's happening.
That's not the right button. Got it?
Okay, that looks good.
Okay, it's the right hand one.
Awesome. All right. So this talk is just largely an introduction to what we're planning to do with a new survey node that was selected in CAN 2, of which I'm the PI. So the node is Project Espresso. It's based out of Surrey Boulder, but we have co-Is at institutions, including Johns Hopkins, Lowell SETI, UMD, PSI, and one at NASA JSC. The project emerged from a conversation over coffee, which is in jest where the name of the program came from. But the driving question in that conversation was, from a number of different angles, we realized we were all asking the same question, which is how do we determine a surface's properties before interacting with it? But it took a while before we realized that we were all asking the same question because there's a lot of ways that you can ask this question. So first off, you have to determine what you mean by a surface. And I mean, in some cases, you mean a potential target. So beyond just a surface, maybe you're selecting which asteroid you're going to go to. Potential landing site on a target. Or a potential sample once you're there. Or potentially, if you're there and you're trying to get somewhere else, you're selecting a traverse and you have to cross a surface to get to another site. Additionally, what do you mean by properties? So basic physical properties, so there's compositional, mechanical, thermal, electrical properties. We're really tackling the first 3. There was no one in that initial group that really worked on plasma properties or electrical properties, so that is sadly something we're neglecting, but is covered very well by other survey nodes. You can take these sort of low-level properties and cast it even further into a more high-level concept like science value or resource potential or operational hazards that are presented by that surface. So, combining your understanding of compositional mechanical can inform your operational decisions based on inference from hazard analysis. And then finally, what do you mean by interacting with it? This is probably the most broad-ranging. So, if you're looking at a surface or you're selecting a sample, you need to know what it is that you're planning to do with that sample in the end to assess or assign a value to it. So how do you select a target or select a site or select a sample before you're taking it back to the lab and spending a lot of time analyzing it? So making sure that those high-level value properties are the ones that the target that you're selecting has the ones that you want. Or before you commit to a traverse. So given those operational hazards, if you're going to go cross a slope with your rover or your astronaut, how do you assess that that slope is safe for a traverse prior to actually committing something expensive or a human life to it? And we came to what became Project Espresso out of trying to assess what we could do to solve some of these questions. So what I'm going to do in this talk is just run briefly over how we're approaching that. We realized that survey was a great place to do it because there's so many different aspects to it that it really requires a broad but highly interrelated interdisciplinary program that combines aspects of laboratory, laboratory research, astronomical observations, instrument design, and field work. So survey is really the only place for which that kind of a broad program is supported and encouraged. We derived from our thinking 3 guiding themes. These are great for organizing once you understand what it is that we're doing, but it's actually very difficult to communicate why we chose them until you understand our goals. It's very circular, but I'm putting them up there for completeness, and I'll maybe come back to them at the end. Instead, what I'm going to focus on is our investigations. We settled on 8 interrelated investigations that are tackled by our team, who I'll introduce in subsequent slides. This got reorganized, unfortunately. They break down into 2 basic themes. So to answer that broad question of how do you determine a surface's properties before interacting with it, the two broad themes that were of investigations that we're pursuing are impacts, impactors, landslides, and ejecta on airless low-G targets, and passive and active methods for quantitative compositional measurements. So the impacts, impactors, landslides, and ejecta come down to what processes are modifying a surface and generating the regolith that you're going to be interacting with, what processes can you use to your advantage to probe mechanical properties of the surface, and what work remains to be done in the laboratory to determine the likely mechanical properties of surfaces. So the investigations that fall under that jurisdiction, I'll introduce the nano impactors in subsequent slides, but this is simply the idea of developing extremely limited instrumentation that is very inexpensive, low mass, low power, that can provide you essentially a disposable means by which you can test the mechanical properties of a surface without committing something expensive or a human life to doing it. Second, informed by those mechanical properties you're predicting from or measuring from the surface, how can you predict actual landslide hazards? So if you're committing an asset or replacing an asset on the surface of the moon, how do you ensure that that site is not likely to be subject to a long-run landslide runout or slope instability? So we're adapting terrestrial landslide hazard analysis tools that the geophysics communities on Earth use to operate in the lunar and small body environments. Back to the understanding what processes are modifying a surface, and additionally, trying to inform future instrumentation, we're working on characterizing impact ejecta dynamics. So this is the case, or this is informed by the knowledge that there are dust detectors that are operating around the moon, or could be operating on a spacecraft near a small body. They're collecting dust from the surface and they can analyze its properties, which you can use to inform things like the chemistry of the surface, or your understanding of the chemistry of the surface, or the mechanics of the surface. However, you need to know what selection effects are at play in terms of what dust is getting to your instrument. And there's a big gap there in terms of saying, I'm collecting this dust in orbit and something is launching it from the surface, but what processes launch it from the surface to get it to my spacecraft are poorly understood. So there's things that we can do to try to understand energetic partitioning in ejecta grains. That flows into low-G gardening processes, which is the processes that are actually modifying and creating the surface that you're interacting with. We're pursuing laboratory investigations to build up an understanding of the low energetic end of low-G gardening processes. And then finally, we're characterizing grain scale thermomechanical properties. So this is the processes by which boulders are turned into dust. And this is one of our interrelated tasks that's working in with some of our laser activated spectroscopy teams. We're using some of our laser rigs to actually break down grains at a grain by grain scale and look at how that progresses. On the other side, the passive and active methods for quantitative compositional measurement. This spans the distance range from we're operating a telescope on the Earth up to we've got an astronaut in the field that's pushing an instrument up against a rock and taking a sample. But we want to make sure that the methodologies that are used here are quantitative and are defensible in terms of making accurate decisions. So the first is to build out our ability to perform accurate target selection and an understanding of potential resource value of targets before we commit to traveling to one. To that end, we are building up a library of optical constants for materials relevant to the surface of asteroids. This is being done at a lab at Johns Hopkins in collaboration with the CLASS survey node, which will be generating a lot of the materials that we'll be testing. For our Pathfinder work, our plan is to really work on characterizing the 3-micron complex so that we can really hopefully build out an understanding of the hydration state of a lot of these minerals that we're seeing with the new spectral observations that we'll be taking with facilities like JWST. So we're accessing the 3-micron complex for a lot of asteroids for the first time without terrestrial atmospheric interference, and we're hoping to sort of front load our understanding of that with this work. The second of these is to say more for near field to actually up close. Looking at laser activated spectroscopic techniques, this ranged from fluorescence and Raman, which is low energy, up to LIBS, which is very high energy, where you're actually breaking down the target. These are very complex material interactions, and the understanding of how materials influence the measurement that you're making is, calling it incomplete is a massive understatement. And you really need a long-term dedicated study to get anywhere in any narrow range of material types. So we're building a laboratory in Boulder to study asteroid regoliths and their response to Libs, Raman, and fluorescence probing, and try to use that to build a database by which you can traceably design future instrumentation to achieve science goals. And finally, we're taking that, that information and folding it into exploration of field instrumentation using COTS, Libs, and Raman devices that you can carry into the field, and determining the exploration roles that these instruments might have. And this is being done in collaboration with several of the other survey nodes. So that's a lot of investigations, and it takes a lot of people to do that. So this is the team that I assembled for this program. We're heavily based at SWRI in Boulder, but about half the team is located at other institutions. Several of you are in the audience. And a few of these people are standouts, unfortunately, not here today, but I wanted to call out Sylvia, who is, if you saw her talk yesterday on trying to understand the 3-micron complex on the moon. This is an example of the work that we're going back and trying to inform with the optical constants work, because right now it's woefully incomplete. Mika McKinnon, who is a disaster mitigation expert, a geophysicist who has worked for FEMA for many years, will be working to inform our landslide analysis work and try to really bring in an understanding of operational means by which you would modify what you're doing in response to an assessment of hazards. And everyone else here, this is just a fantastic team. I'm extremely excited to work with them for the next 5 years. And then a laundry list of collaborators. There's a few interesting institutions here that I'll bring up later in our partnerships, including Planetary Resources and Integrated Spaceflight Services, and a number of people that you've seen around the meeting today, simply because we have partnerships with 5 of the existing survey nodes that were baked into our original plan. So I'm going to wrap up in what time I have remaining, which is how much time? 1 minute? All right. Then I'll just talk about what I think is the coolest thing, and it's the thing that I'm leading. So, and it's also the one that I think the most... Default. Yeah, exactly. So this is also one that I think is going to have the broadest utility in terms of where other people in survey might be coming in and trying to use this. It's one of our largest investments. It's the Airborne Space Environment Chamber. So to really get at those low-G gardening processes, to look at regolith interactions, and to do some instrument testing, we are building a new vacuum chamber. Of the current specs are about 36 inches by 6 feet, that will be mounted inside a microgravity aircraft. So this is to provide a truly a large chamber within which you can do regolith interaction experiments without strong edge effects under microgravity and vacuum conditions. So if you're really trying to push down to low energy collisions, or you're looking at things like wheel interactions with the surface, or sampling hit interactions with the surface, you need that truly relevant environment. We haven't had this capability since the 1960s. And we're hoping to turn this back on. The chamber I'm showing here is a chamber that was built in the early 2000s to do this, but it never flew. The aircraft that we'll be performing this with is the Canadian NRC, CNRC's Falcon 20, contracted through Integrated Spaceflight Services. We're currently planning somewhere between 10 and 12 flights over the course of 5 years, with the nominal experiments that we have planned for the investigations that I outlined. However, it's a large chamber, and a number of those experiments aren't necessarily going to take up the entire volume. So if you have thoughts on experiments that require a relevant environment to small bodies that are looking at regolith interactions, please come speak to me. Beyond fitting into those flights, it would be easy for us to adjust our manifest and work with other survey members and people from the community to enable further exploration. So with that, I'm going to put up my summary slide and take any questions.
Thank you very much, Alex.
I probably don't need to.
Yeah. You're getting it.
Oh, and it's even on, and I always wanted to be able to catch something. So you mentioned, I think it's your 3rd investigation about which is geared for answering uncertainties about the dynamics of how stuff comes off of a surface. So it puts me in mind of Sasha Kemp's instrument on Europa Clipper, which depends on that, right? So to what degree is the research that you guys have not yet done enabling for his instrument to do the science he's promised to deliver?
We had well, see, not being familiar with their trace matrix, I don't know if there is something that there's a gap that they need filled. I suspect not. So for our case, there are strong selection effects in terms of what they're getting off the surface of Europa. But if it's a bit flip in terms of saying, you know, we're looking for a particular material, if that shows up, great. If not, that's not a problem. Or there's some absence that we have to understand. Then I don't think it's super important to understand the selection effect. It's really when you're trying to go back and do like a debiased analysis of the composition of the surface based on the grains that you're getting in orbit, or of the mechanical properties of the surface, that you really need to understand the selection effects. Now, there could be some of those hiding in the Europa studies. I'm not familiar with them, but absolutely, this is the instrumentation that we're planning to use. It's a means of doing non-intrusive, non-destructive dust dynamics in situ. So we can put this in an impact experiment and actually analyze the velocity distribution of dust coming off, the composition of that dust grain by grain, and the spin state and the shape and size of every grain. So that really gives you a holistic picture of the dynamics of the dust that you're creating in an impact experiment.
Thanks.
Okay, we're going to have a discussion session a little later on as well. Thank you very much, Alex. Appreciate it. Very exciting.